Thank you to everyone who has joined us for the CGIAR Crop Damage Classification Challenge, um, sponsored and hosted by IFPRI, Acre Africa, Culro, and the CGIAR Research and Initiative and Digital Innovation. This is our second challenge hosted in collaboration with these partners, and yeah, what a privilege. I'm going to invite Berber Kramer from IFPRI to tell us a bit about IFPRI and the impact she sees this challenge and the previous challenge having.
Thank you so much. Yeah, so my name is Berber Kramer, and I'm a senior research fellow with IFPRI. I'm based in Nairobi, so calling from Kenya. It's great to see so many people online. The reason for why we're excited working with Zindi is that we've been testing for quite a while now, since 2016, innovative ways to strengthen agriculture insurance. So IFPRI's mission is to provide policy solutions that reduce poverty and end hunger and malnutrition. And as part of that, we are closely working with partners, including on strengthening agriculture insurance. For instance, one of the things that we've been working on, and that's really the setting of this challenge, is developing what we call picture-based insurance to strengthen agriculture insurance, to help farmers de-risk agriculture and invest more in their farms with greater confidence, not having to worry that extreme weather is going to damage their crops. What we see in existing insurance solutions is that too often insurance products rely on an index, such as a rainfall index or a vegetation index, that doesn't always trigger a payout when farmers' crops are actually visibly damaged. And you can imagine this is a big frustration for farmers who have maybe, paid a good amount of money to get an insurance policy in the hope that it would secure their investments in their farm, and then crops being damaged and not receiving a payout has been a big frustration. And so in 2016 in India, we started testing an approach whereby actually in those types of cases, farmers can send in images of their damaged crops. And experts looking at those crops, at the images and saying, okay, yes, we can see, your crop is visibly damaged. The index insurance policy didn't trigger a payout, but let's give you a payout because we can see that your crop is damaged. So that's a solution that we've been working on first in India. And through that, many images were collected. And I don't know, some of you might even have participated in a Zindi challenge 2 years or 3 years ago, I believe, where we asked data scientists participating in the Zindi platform to predict growth stages of wheat for these cases in India. And then after that, we've, evolved and collected thousands of extra images through a partnership with Acre Africa. And Acre Africa, Benson is here. I will tell you more about the organization. But what's really key is that Acre Africa is an organization that provides insurance and other agricultural risk management solutions to farmers across Africa at a very large scale. And so having individual experts looking at each and every image to assess whether those crops were damaged. As we were entering an impact evaluation with Acre Africa of this new insurance approach, we quickly realized that it wasn't going to be scalable in the way that we're doing it with these manual expert loss assessments, and that the approach needs to be automated. Now, we have been working on using convolutional neural networks to automate the process. But so far, in working with our machine learning partner, we haven't had great success in predicting the types of damage from the existing image data sets that there were. And particularly one challenge was the transfer learning piece. So we would be able to get high accuracy for models within a given season, but then when images for the next season were coming in, it was much more difficult to predict crop damage with high accuracy for that next season. So that's some background behind why we're doing now this challenge. We would like to challenge you to come up with better solutions than the machine learning solutions that we have now, using your toolkit. So we're very excited to see what types of models and approaches you might come up with. And the reason why IFPRI is sponsoring this challenge for a solution that Acre Africa as an insurance provider in the end will be using is that we find it really important at IFPRI and within the CGIAR to make sure that any solutions that we work on, that our partners are later also able to use those solutions. So the usability of the models that are going to be developed through this challenge is going to be super important. We also hope that there will be engagement between the winning solution, the winning teams, and Acre Africa to integrate the solution in Acre Africa's digital platforms. And because only through that channel, I think this can have real impacts. Now, at the same time, the reason we're working with Zindi is that it's a platform with a lot of people, a lot of talent from the continent where we're working. And we're really hoping that this is a learning opportunity, but also an opportunity to showcase that talent. And so because of that, also, we're using our, public funding to support this challenge. And we're hoping that, a lot of good comes out of that. And so, I invite you to go and beat the existing models that we have already, and see, really excited to see what comes out of it. So with that, I'll turn it back over to you, Amy.
Amazing, Beba. Thank you so much for sharing. It's not often in the real world you get to see your solutions get put out into the wild, and sometimes on competitive data science platforms you don't get that opportunity. So I really look forward to the winners and the owners of the solutions putting them into the wild, hopefully monitoring them and tweaking them to fit your pipeline. And I love it when the Zindi community can beat what people have already made. Benson, I would like to invite you to tell us more about Acre Africa and the impact you see this solution having.
Thank you very much, Amy. Thank you for the organizing this and for Zindi. I think I'll introduce Acre Africa and move on to discuss a bit about this product and why we're excited. I think Dr. Barba has mentioned a lot of it, but I'll quickly highlight. So Acre Africa is an insurance intermediary sitting between insurance companies and the clients. So most of the time we work with aggregators and we work directly with the smallholder farmers to provide insurance solutions. As Baba has said, we saw a problem in resilience where most farmers rely on rainfall to produce. But then we know there's been a lot of changes in the climate change, and this has really brought about irrational patterns in the rainfall, which are now not very predictable, and also adverse events like drought or excessive rain. So we were solving this using traditional insurance solutions. For us, particularly, we were using parametric, which we were looking at the index of rainfall, looking at the soil moisture index. But then we realized a challenge with the index is not measuring some things that are happening actually on the ground. Things like the pests and diseases, and some nutrients deficiencies, yield, things that may not necessarily be determined by the index. And with that, with the help of CGIAR, IFPRI, through R&D, research and development, we took on the challenge to use the solution of picture-based insurance, which is where we have a team of village-based champions. These are mostly lead farmers who work with groups of farmers in their locations. So they would take pictures, and these pictures would go to the back end, and our teams would be involved in reviewing and say, okay, this one has loss, this one doesn't have, and convert that into quantitative data, which was then used to complement the index and now provide an insurance cover. So for the pictures, we would get a lot of pictures, and the manual process of labeling and saying this is what and why was really tedious, and that's why we moved to machine learning. So for us, we are really excited to see this is a shift which would really transform the industry, because now the pictures would be able to help us. And our focus is majorly on two things. Being an insurance intermediary, we would want to see better insurance products. So out of the pictures, once we collect enough information, and over time, then this can even become a standalone product in future. But currently, because of regulation, it requires to work with another insurance product like an index one. So our aim is to see it do that, where machine learning can help us convert these to quantitative insights that make sense and can be used for the pricing and the monitoring, and as well as automated advisories. So for all the farmers that we work with, we have constant advisories in form of to ensure that they avoid the risks. For example, risks of something, a weather event that is abrupt. But using pictures, would want now the interpretation of the picture to determine what it can see, and use that to send advisories automatically. So this is the bigger picture we see, and we are happy to see many people interested. And so we will be looking forward to see the models that really are able to provide the eyes on the ground. And with that, thank you, Amy. Back to you.
What an apt name. You don't need to explain the project. It's eyes on the ground. And I love the idea of personalized advice given back based on their crops, instead of just generally there's been a lack of rainfall, but what's specifically happening with your crop. And I think that's so important. I have popped a message in the chat, but please do write down any questions you have for Berber and Vince, and we will have a Q&A at the end. We will also be going through a starter notebook for this competition, so please remember any questions, and we'll go through them at the end. I'm now going to share my screen, and I'm going to walk through the challenge on Zindi and where to find it. I don't think I've introduced myself yet. My name is Amy Bray. I'm a data scientist at Zindi. So if you go onto Zindi, you would need to go onto the Compete tab. You're going to scroll down to the CGIAR Crop Damage Classification Challenge, which has a whopping $10,000 in prizes. So I think it's a well worth challenge signing up for. Over here, there's an explanation of why this is important and how your solution is going to help the client, help ACRE and help IFPRI. And the objective of this challenge is to create a machine learning algorithm to classify a crop into multiple categories. Does it have good growth, drought, nutrient deficient, weed, or an other category? Other categories involve pest, disease, or wind damage. Data for this challenge was collected using smartphone images. The evaluation for this competition is log loss. There's a clause over here that I want to make very clear. Values need to be between 0 and 1. But please do not set thresholds or round your probabilities. So as you can see in this row over here, we've got a 0.92, which means the model is 92, pretty certain that this image is suffering from an other category. Please don't round it up to 1. Please leave it as 0.92. This is important for the client to set their own thresholds, because maybe 0.92 is not certain enough for them. Maybe they need a 0.98 before making that decision. Another thing I'd like you to pay attention to is compute restrictions. Your model needs to take a reasonable time to train and run. This is to ensure that the models can be retrained relatively often, and that the inference time is quick. So we set a reasonable time at 9 hours on this type of machine. It needs to be a single GPU machine, for an example, an NVIDIA P100. With that reasonable time, it should take about maximum 8 hours to train and 1 hour to infer. We are currently doing code review for the first challenge, and we are really have hit a roadblock over here. Or not a roadblock, we are taking this very seriously, as this is important to the client. So please do adhere to these compute restrictions. Prizes, 10,000 prizes. When you submit your solutions, you need to include documentation so we know what and why you did the method you chose. And you need to adhere to those compute restrictions, as mentioned. There are 10,000 Zindi points available. You can read more about Zindi points and why they're important over here. This competition runs over the holiday period and closes at the end of January, so you have lots of time to improve your model. We've already said thank you to our organizations who have sponsored this competition, but here they are again. So thank you to IFPRI, ACA Africa, CALRO, and CGIAR Research Initiative in Digital Innovation. If you are new to Zindi and you don't know how to start, we've set up a couple of videos for you: how to enroll in your first competition and make a submission, how to create a team. Please note, for competitions, you need to form a team before the last 5 days of the competition. You cannot create a team in the last 5 days of the competition. And how to update your profile if you want to change your country or your university. If you don't have Python on your local machine, you can use Colab. And here are 2 videos that show you how to use Google Colab, which is a product by Google. I think they have recently allowed you to start coding in R, although I'm not too sure. So you don't have to have Python or fancy anything on your computer. All you need is access to the internet. For the rules, you can create a team of up to 4 people, but please do not collaborate outside a team. If you want to share code with someone outside your team, or advice or insights, please share that on the discussion board. Please only use publicly available packages and open source packages. And only use the datasets provided for this competition. Don't go searching for additional resources online to supplement. Please do not add the dataset to any public domain so that they're sharing, such as Kaggle or GitHub. Please ensure that the data remains private and it doesn't contravene Zindi's rules. And then submissions and winnings. You can make 10 submissions per day and 300 throughout the competition. And before the competition closes, you need to select your 2 best submissions. This is to ensure that your code is reproducible and also that you back the model that you've created through experimentation. If you are in the top 10 at the end of the competition, you will be required to submit your code so we can code review it, make sure that it adheres to the compute restrictions, doesn't use any external data, and produces your score on the leaderboard before we hand over prize money. Where to find the data? If you click on the data tab, you can find out more about the data. If you scroll down, you'll see that there's no zip file that contains images. Don't panic. There's this crop damage classification data download. You need to download this Python notebook. You can open it in Colab, and you'll be able to download the images. Please take note that this takes about 2.5 hours to download on Colab. There are lots of images, so don't stress if something's taking too long. I'm now going to hand over to Nelson, and he's going to walk us through a starter notebook. I see that there are some questions. I'll read through them at the end of the notebook sharing session. We can go through them. Nelson, do you want to share your screen?
Of course. Just 1 minute. Can everyone see my screen?
Yeah, we can see your screen.
Perfect. Hi everyone, my name is Nelson. I'm a data scientist at Zindi. I work with Amy on preparing some of the challenges and some of the and reviewing the solutions once the challenges close. And today we'll be going through a starter notebook to get us familiarized with this challenge. I think from the beginning, it's been clear that this is a computer vision challenge. And so for the purpose of this competition, we'll make use of several computer vision tools. And just to begin with, it is always important to make sure we have everything we need before even importing the libraries. And for this challenge, this particular notebook, we're going to be making use of image or computer vision models, and we'll be installing a library from PyTorch known as PyTorch image models. This contains various resources that will help us build the various computer vision models that we'll make use in our solution. So I will not be running the cells in this notebook, but we will share this notebook at the end of the presentation, and so you would have enough time to play around with it and get familiar with the solution at your own pace. And once we have the library installed, we're going to call a few of the CGIAR tools that we're going to make use in our solution. And we'll be building models using the FastAI library, and we'll be making use of the image models from PyTorch to run our solution. We'll make use of the pandas library to manipulate or go through the data set, and it will help us read the data or sort of align the data from where they're stored in our database or in wherever we've saved the images, and load them up to put them through the model. Some other libraries that are important is the NumPy library that is very useful for linear algebra and manipulating data. We will also be doing a k-fold cross-validation, which is a tool that is used to ensure robustness of our model, to make sure that the model is not overfitting all the data. And for this particular challenge, we'll be making use of a stratified k-fold that is going to divide up our data into sections based off of strata or groups that are related to the target. I think Amy mentioned it's important that our code is reproducible, and for that we need to set the seed, and this is a random number that will ensure any of the processes that involve randomness are pseudo-random, meaning they are reproducible. Anytime anyone gets a hold of this notebook, they will be able to run that code and get not perfect, but near perfect results, or as close to the results I'll be getting as possible. And the reason why I say as close to as possible is because once you start working with neural networks or with GPU supported libraries or tools, reproducibility is not guaranteed, but it can be ensured to a certain extent. And so we've mentioned we'll be making use of k-fold cross-validation. And so we will be specifying the number of folds, and these are essentially the number of this represents how many times our data is going to be split up. So if we have a train set of, say, 1,000 rows, let me make it a number that can't be divisible by that. Let's say we have a data set of 1,800 rows, and if we're making use of a threefold cross-validation, it means the data will be divided up into 3 parts, and each time it will be trained on 1 or 2 parts, and the part that's left out will be used as a validation set, allowing the model to train on a specific set of the data set and test on a data set that's not been seen before. This ensures the model doesn't overfit, as mentioned before, and also generalize well in instances of like new cases or different seasons or different variables. And batch size, if you are familiar with training or neural network or neural modeling, we usually train the models in batches because most often, and it is in this case, the data sets are huge. And so it's important to break them down into chunks, and these will be passed into the model one at a time in a pre-specified batch size. And this is determined partly by the resources you have. And for our case, we'll be making use of Google Colab. And for Colab, you have different tiers, and how each tier allocates a specific amount of virtual memory. And so we can experiment with this number to see how far you can push it. Generally, a bigger batch size means better performance of the model and faster training, but at the cost of more resource consumption. And as Amy mentioned, it's important to adhere to the requirements of the challenge, just so the solution is as useful to ACRE and the CGIAR research group as possible. And so also in a computer vision task or modeling task, it's important to always standardize the images into a specific size. This is to ensure that each image that goes through the model is of a standard quality and size. And so the model can more accurately summarize the information on every image and compile them and develop or enrich the weights that are in the network, in the deep neural network. In the process of training, we'll be training several times. We'll have the model go through the data several times so that it is capable. It enables it to update its weights and get to more general or more a better fitting position, where it can more accurately look at any image and precisely or more accurately predict the kind of damage that exists, for instance. And so the iteration is done in epochs, and we will specify how many epochs to train. This is also a number that is important to experiment with. There is no rule, but it is also limited with resources, and especially with like training time. So the more epochs you put in, the more training time is required. But also, the longer you train, potentially it's the better the model learns, but it's also potentially the more overfitting your model is going to be. And for this variable, this is the initializing learning this is a learning rate at which we're going to initialize our model. Because with the library that we're going to use, it's going to use a variable learning rate where it will try to change or lower the learning rate. So the model, as the model learns or continues to learn, it's going to slow down the pace or the rate at which it's learning. And so we're going to start it off at, I think this is 0.00002, and the learning rate will continue to reduce until the model reaches a global minimum. The number of workers is just the number of processors that you have in your machine. You can set it to as high as your machine is capable of handling, but ultimately, if it's over your capabilities, then the machine itself will just adjust to whatever it can. The patience, I think, is another variable that is inherent to the library that we're using, where this is the number of iterations that we will take before updating the learning rate, I believe. And for the model base, this will specify the model that we're going to use. And in our solution, we're going to make use of the solution. I'm not sure how to pronounce this, but this is one of the more powerful convolutional based image models, and it is trained on the ImageNet data set, which is a data set of thousands, maybe hundreds of thousands of images that have up to 21,000 classes. These were models that have been trained. I believe this was from Facebook, where you have, these are research groups with massive resources that decided to train massive models on huge images. And as Berber mentioned, the ability to apply transfer learning, it makes this a very interesting challenge. And so a good example is what we're doing right now. This is transfer learning. We're going to use the convex model, which it has been proven to be the more superior model of any iteration of visual models. And so we're going to transfer what it learned from this huge data set onto our task of a relatively smaller data set, but potentially the model learned enough patterns to accurately capture the patterns that exist in the crop images that we're going to pass through the model. And so just to go through it a bit quickly, we're going to specify the location where, or at least once you go through this notebook, you're going to have to specify where the data is stored. And remember, we specified the seed. This is any number you can put in. I usually just put in whatever time it is, so I can even update this right now. And I guess depending on where you are, it's going to be something like that. And once you have the seed specified, you're going to set it. And this will ensure any random process that will be running in our environment is going to be pseudo-random, meaning anytime anyone runs this model or this notebook, they're going to get the exact same results. So we're going to dive into pre-processing, where we're going to prepare the train data and get it ready to pass through the model. I like doing this using functions because it allows for, and you definitely could start a bit rougher, but once you have a good workflow, it's always nice to sort of organize your code into functions. And later on, if you can, put it in classes, just because this makes, it also adds to the component of reproducibility, where you can always just call the function and pass in the arguments and get a clearly defined output. And so in preparing the data, we're gonna get the image ID, we're gonna drop the duplicates from the data sets, and we're gonna change or specify the target. And this is the damage column is gonna be our target. And we're going to split it up. Remember, we're going to be making use of k-fold cross-validation, and we're gonna specify different parts of the data we're gonna allocate different parts of the data to different folds. And so after that, we're gonna print out how many data points are in each fold, and the remaining steps are definitely just us first assigning the path or attaching the direct path to the data, to the file names, meaning once you, and sorry, I don't have the data right now, or once you go through this data, you'll notice that the file name column only has the image file name. And so what we're doing with this line of code is we're attaching the entire directory onto that file name, so that once we pass this data frame through the model, it's going to read the entire path and go fetch the images from where they're stored. And so the metric for this challenge, definitely not the RMSE, but we're going to have to update that. Maybe even comment it out. But yes. So we're going to move on to training the model. As we said, we're going to use a cross-validation, a k-fold cross-validation. And so we're going to iterate through the folds. And each fold, we're going to pick out the part of the data that is related to that fold and specify the validation set. In this case, we're going to assign a validation marker to every data point that is in the validation set, or that's in the fold of the validation set. And we're going to create an image data loader. And this is a tool that is from the FastAI library, where it's creating a specific class or object that loads the data, the images from their locations, as well as the targets, and makes it easy to pass the images as well as the targets and train the model. And so this object reads from the data frame, and this is definitely why we had to prepare the train data. So we're going to pass in the train data frame, and this argument points to the column, or once you specify this argument, it's going to tell the data loader which column is it should be looking at, or to identify the validation set. And we're going to pass in the seed, because training the model is a random process, and we're going to have to set a seed in order to make it more reproducible. And the FN column is the file name path. If you can recall earlier, we were attaching the entire path onto the file names. And so this argument tells the data loader where in the data frame to look for, what column in the data frame are the file paths specified. And the label column, we specified the target to be the damage. And this is perhaps one of the more important variables. This tells the model what kind of modeling you're doing. If this was a regression task, I think it would have been a regression block. But since we're doing a multi-class classification, we're going to have to go with the multi-category block, which essentially is a classification task. It tells the FastAI library that we're doing a classification task. And as said before, we're going to pass the data in batches of predefined size. And for our case, we're going to make use of 16 images per batch. And we're going to set the number of workers, and we're going to resize the images according to the predefined size we specified. And so one thing with computer vision is it's not enough to just pass in the images. It's always useful to transform them in a way, or in different ways, where you can stretch them, you can rotate them, you can flip them, you can augment them in different ways. And this, or you can even change the brightness and the contrast. And this is useful to the models so that any image that it sees, regardless of its orientation, its color, its brightness, it will be able to detect the features in that image, if that makes sense. And this sort of helps it generalize better so that it's not surprised. Maybe you have the same or similar images of a crop with a certain disease, but only because it's tilted at a certain angle, then the model fails. And so this argument passes, or essentially tells the tool that we're going to apply these set of transformations where it's going to adjust the brightness and the contrast, and it's going to flip the photos or the images around and rotate them at different angles so that the model can get accustomed to the different orientations of the images and better capture the patterns in the data. And so once we've specified our data loader, we're gonna create our model. And all these items are from the FastAI library. So this line of code essentially calls everything from the vision package in the library. And so all these, the data loader, the create model, the learner, these all found in the vision package of the FastAI library. And so we're going to create our model and we're going to give it a name. I believe we've specified this model. And once we create it, we're going to specify that it is pre-trained, meaning that we're not training it from scratch. We're just going to fine-tune it using the current data, or maybe not even fine-tune it. We're just going to pass the data through the model and have it give us results, because the model weights are already pre-trained on old or like on a massive data set, and it should have it should be able to capture the patterns in our data fairly accurately. And once we've created the model, we're going to pass it through the learner, and the learner is gonna essentially, the learner has different components, and one of which is specifying what the loss function is, what the metrics are, and this will help in tracking the performance of the model, or in keeping track of how the model improves over time. And once we've specified the model as well as the learner, and do notice that we're going to pass both the data loader and the model through the learner. And once we have the learner, we're going to fit it onto our data by specifying the epochs and initializing, or specifying the initializing learning rate. And we're going to pass a few more arguments. And I do recommend reading through the FastAI library and getting familiar with some of these things, just so you're more comfortable experimenting with a notebook like this. And once we fit it, we are going to save our model for later purposes. And afterwards, I did mention I love using functions. And so this is just the training function. And so this is the prep. We're going to prep the data using the preparation function, and we're going to train the model using the train function. And it's going to go for a couple of epochs. If you do notice it taking a bit more time, you probably want to play around and reduce the number of epochs or reduce the batch size and see how that works for you. And once we have our model, we're going to run it through our test data. Once we're comfortable with the performance of our model, we're going to run it through the test data, and it essentially looks very similar to the training process. We're going to specify the data loader in a very similar way to the training process. We're going to specify our model. We're going to pass the model and the data loader through the learner. And once we have the learner, we're not going to fit it this time. We're just going to load our model weights. And once we have that, we're going to specify, or we're going to pass the test data frame onto the data loader. And then we're going to use the learner to predict on that test data set. And we're going to get a few predictions, or we're going to get predictions based off of the model's training process. And afterwards, we will put those predictions in our data frame, and we're going to save it, and that will be ready for submission. And I think Amy went through some of the rules or the guidelines towards submissions and how to make submissions. And essentially, once we have the CSV file and plug it into the Zindi platform, you're going to get a score that's going to rank you on the leaderboard. And based off of that ranking and that score, you're going to come back and experiment and try and figure out better ways to design your model. This is one way to go about it, using the Fast AI library. It's fast, it's quick, it's efficient, but there are vast libraries out there. There are, as we mentioned before, we're using image models from PyTorch. PyTorch is a one of the more famous libraries or backends used in deep learning, and it has its own set of tools that you can play around with to figure out a challenge like this. But yeah, I will say that is the end of my presentation. I will hand it back to Amy, and I do hope it's helpful.
Amazing. Thank you so much, Nelson. Nelson, I'm going to ask you to continue sharing your screen in case anyone has any questions specific to your code. But I'm going to start off at the top. Mayura has asked, what is the expected inference time per image? For example, less than 1 second, less than 10 seconds. If I am not mistaken, I think there are about 5,000 images in the test set, and there are 26,000 images in train. So altogether, train and test means to take you 1 hour and 9 hours. Apologies. We've recommended that you split that up into 8 hours train, 1 hour test. And so that means 5,000 images, 3,600 seconds in an hour. So inference per image is probably going to be less than a second. However, you can train for fewer hours and infer for longer. Always a shorter inference time is preferred, but whatever lets you win the competition. Samir, good question. Could you kindly explain how to add documentation on Zindi? Zindi doesn't have a function for you to add documentation. However, when you create your notebook, you can jot down some notes in your notebook right here. And when you make a submission on Zindi, there's a place to write comments. So you can put your notebook name or the notebook version in that comment section. You can even write some comments there. We also recommend using GitHub just to track your versions. However, the most important part about documentation is if you are in the top 10, and we recommend it to everyone because there are times when we go further down the leaderboard, is to document your solution. There are some blog posts on Zindi that explain what is good documentation. There is also lots of documentation on the internet. Normally, good code doesn't require comments and documentation, but just be safe and write documentation. An example of documentation would be, I used this type of hardware. It takes this long to run. The objective of the code is to do this. A high-level overview does this. And so that means a manager or someone can quickly come in and look. And then your next page of your documentation, you go in a bit deeper. And that allows the data scientist or the data engineer who's going to be implementing your solution to really understand what's going on. Nelson, I'm going to ask you to comment on this question from Mayur. Under the data tab, it states, when you download all 30,000 images, take care when building models to account for the zero inflated datasets. Could you please explain what a zero inflated dataset is and how to take care?
Yeah, of course. I do believe this was transferred from the previous challenge, where the challenge required prediction of the extent of damage. And so in that in that competition, we had several data points that had a lot of zeros because they were not draft damage. And that was, so this is a bit of a carry forward, or like it definitely isn't something to worry about in this challenge, because we're working with the damage types, not the extent of damage. But yeah, we missed that and included it in this challenge's rules. But yeah.
Could I chime in there?
Yeah.
Please do.
Okay. So one of the things, though, I think to keep in mind is that some categories are going to be more common than other categories. For instance, good images are probably going to appear in the data a lot more than images that have been classified as reading problem. And so that is something to keep into account as you're working on solutions and thinking of what is the most useful solution. Because there's two solutions that would generate an equal accuracy or an equal performance metric. But one is actually predicting those categories that have very few observations more accurately, then that would be a preferred solution in a way, more impactful. So I think that's important to keep in mind from sort of the, what's the chances that this solution is going to be used. Yes, it's very easy to predict the good images because there's a lot of them. And so an algorithm that would, put everything to good would actually attain pretty high accuracy, but that's not the solution we're looking for. That wouldn't require, data science. So it really is about also being able to predict those less common categories. And so there's some imbalance in the data to keep in mind.
Amazing. Thank you so much, Beba. Maya, please can you unmute yourself or just comment in there if you've got any further questions regarding that?
Well, yeah, all good. Thanks.
Amazing. Samir has asked, is it possible to go through some samples from the data set to understand what a specific category is or what good and what damage looks like? He's asking because he's not familiar with the agricultural domain. Samir, I'm in the same boat as you. I'm definitely not in the agricultural domain. We don't have it in this notebook. However, this notebook will be uploaded by Monday. And in this notebook, we will include a cell that shows you how to visualize the images, especially the images from the train. And we'll also show you how to visualize the images with your predictions, so that you can see, like, did your prediction predict the right thing, or as a human, can you visually see? We'll also include these on the competition pages. So if you wait until Monday, you'll be able to see some imagery. And then I'd love to have a discussion with you on the discussion board. Was that useful? One of the things Benson and Berber mentioned is the need to have experts spend time manually going through these images, and could a Zindi solution and a machine learning solution speed that process up. So you do need an expert eye to really figure out if it's between two cases that are really close together. And we've got a question from Samaka. Are we only allowed to use Fast AI? Fast AI is a solution, is a framework you can use. You do not have to use it. This is the brilliant part about Zindi, and that the community and the leaderboard is that the best solution ends up winning. And that might not be fast AI. It's up to you to do experimentation. What other frameworks are there out there that you can use that work with the hardware restrictions? And then just to confirm, this notebook will be provided on Monday, and it will include updates on how to view a sample of the images, just so you can see what a damaged or healthy crop looks like. So Marco, please can you comment, unmute yourself if you've got any questions, would like to add anything further. And same with you, Samir. Oh, that's such a good question, Samir. So, Berber, I think this is a question for you. How was the data labeled? For example, if the data is labeled as disease, what do the data labelers look at in the image to determine the label? Do you know?
That's a great question. Vincent might be able to say more on this too. But these were agriculture experts looking at the images. Drought would, they would be looking for signs of drought. So for instance, a yellowing plant, but not ripening. So just looking for yellowy pictures isn't enough, because looking for yellow would mean that you're also picking up ripening crops that might actually be doing very well. If you're thinking, for instance, of maize that gets yellow as it's ripening. So these experts, with the human eye, they were able to look for those nuances, which is why we can't just have an algorithm that looks for yellow. In terms of diseases, they would be looking, for instance, in the leaves, there might be a discoloring, or in the stem there might be discoloring. Pests is typically like if you have the leaves, there might be sort of pieces in the middle of that leaf missing because the pest has been eating into it. Sometimes like visibly the bugs sitting on there. I think there's documentation I'm seeing that you're saying, could you show that in the image? I can't show examples right now, but there's documentation online, also to papers, where more of this is shown. And I can see with the Zindi team if perhaps, we can also put a PowerPoint online, which has a little bit more of an example of images. I think in general, I'd say use the labels that are provided in the data set, for the training data that you're using. We're not asking you to be agriculture experts to actually then be labeling any images yourself. I can understand that you'd want to see some of the images and have some intuition behind it. So we'll see what documentation we can put up online. Don't worry about that piece, that component, too much, because it's possible to do the challenge without being an agriculture expert and being able to label the images yourself.
Thanks, Berber. Nelson made a comment while going through the notebook that there are a lot of images, and you might be. I was in the same boat where I went, oh, why is there so much data? Why can't this just be nice and simple and small data? But I just want to remind you what a privilege it is to be able to work with so much data. You also don't have to work with all of the data, as Nelson showed, that you can segment the train data and only train on certain segments. So that is a way to reduce training time and to increase experimentation, like the experiments you can do. I just want to remind you about what a privilege a lot of data is, and how lucky we are in an African context context to have all this data. We are 5 minutes over the time. However, if there are any more questions, I'd love to answer them. So please pop them in the chat. Please can you unmute yourself? I'm going to just sit in silence for the next minute. So please raise your hand, put it in the chat, and if there's nothing, we can end the webinar. Just to reinforce, this recording will be on YouTube and will be on the competition page on Monday. And the notebook will also be on the competition page on Monday. So you don't have to memorize any of this. It will be out there. And then, Samia, as requested, we will put in the notebook how to visualize, just so you can see what the images look like and what they're labeled. And then just to reinforce, experts label them. And we don't expect you to be an expert in the next 2 months. We just expect you to do what you're good at, which is data science. It looks like there's no further comments or questions. So I'm going to let you know our favorite quote at Zindi, which is there's no losing, there's only learning. So please make a submission on the leaderboard and grow with us. Cheers.
Thank you, Amy.
Yes, thank you, Amy.
Great. Cheers, everybody.